Welcome to our journey through the nuclear atom. In this explainer, we're going to explore how discovering the absolute tiniest building block of the universe literally changed the course of human history forever. We're talking about a wild ride from early, kind of comical theories all the way to the heavy-hitting science that powers both stars and modern cities.
But hey, before we zoom into the hard science, we really have to acknowledge the immense human stakes here. Now I am become death, the destroyer of worlds. That famous, chilling quote from J. Robert Oppenheimer, one of the leading minds on the Manhattan Project, reminds us that figuring out the atom's structure wasn't just some abstract academic exercise. It ultimately gave birth to humanity's most devastating weapon. We have to remember that the discoveries we're about to look at happened during the early 20th century. That was a time of massive global conflict, where unlocking the secrets of the atom literally meant holding the power of life and death.
All right, let's jump straight into Section 1, Seeing the Invisible. So using modern technology, specifically a scanning tunneling microscope, we can actually see individual atoms now. What you're looking at here are silicon atoms. Yeah, the exact same material your computer chips are made of, but magnified a mind-blowing 100 million times. To give you a real sense of just how unbelievably tiny these things are, if you line them up, roughly 4 billion of these atoms would fit into a single meter. 4 billion.
Which brings us to a really fascinating question. If we need highly advanced microscopes just to see the blurry outline of an atom today, how on earth did scientists back in 1909 figure out what was happening inside them? I mean, they couldn't just look through a lens to see the internal structure. Instead, early 20th century physicists had to act like scientific detectives. They used incredibly clever experiments to deduce exactly what they couldn't see.
Moving on to Section 2, Smashing the Plum Pudding.
This right here brilliantly illustrates the contrast between what we used to think and what we know now. On one side, we have J.J. Thomson's idea. So after discovering the tiny, negatively charged electron, scientists reasoned that, well, since atoms are electrically neutral overall, there must be a positive charge balancing it out. Thomson basically imagined a sphere of positive charge with negative electrons just stuck into it, kind of like plums in a pudding. But then Ernest Rutherford and his team came along and proposed the nuclear model you see on the other side. This is more of a solar system vibe, with a really dense central nucleus and electrons orbiting around it.
So how exactly did Rutherford prove that plum pudding model wrong? Well, he did it through one of the most elegant experiments in all of physics history. His team fired these tiny, extremely fast, positively charged alpha particles at a piece of gold foil that was literally only a few atoms thick. Now, based on the plum pudding model, the positive charge was supposed to be spread out, right? So they expected these fast alpha particles to punch straight through, just like bullets through a cake. And honestly, most of them did. But here's the surprise. A few of them were dramatically deflected, and some even bounced almost straight back. The sheer shock of this result is captured perfectly in Rutherford's own words. He literally said it was as if you fired a massive 15-inch artillery shell at a piece of tissue paper and it came back and hit you. No way, right? But this single incredible observation proved that the positive charge and almost all the mass of the atom weren't spread out like a soft pudding. Instead, they were concentrated in a tiny, incredibly dense, positively charged region right at the absolute center of the atom. And that, of course, is what we call the nucleus.
That leads us right into Section 3, Inside the Nucleus.
Before we just list out the parts, we really need to grasp the mind-bending scale we're dealing with here. We just learned the nucleus is tiny, but exactly how tiny is it? Well, imagine taking the nucleus of an atom and scaling it up to the size of a 1-centimeter glass marble. If you place that marble right at the center of a football pitch, the tiny electrons would be orbiting all the way out at the very edge of the stadium seating. It's crazy to think about, but this brilliantly illustrates that when you stub your toe on a rock, both the rock and your toe are actually made up almost entirely of empty space.
So what actually occupies that tiny bit of non-empty space? This table breaks down the 3 subatomic particles you really need to know. Inside that tiny central nucleus, we have what we call the nucleons. Those are heavy protons carrying a positive charge and equally heavy neutrons carrying absolutely no charge at all. Meanwhile, zipping around in that vast empty space outside the nucleus, we have the electrons. They carry a negative charge that perfectly balances out the protons. But check out their relative mass. They are practically massless compared to that heavy nucleus.
All right, let's look at Section 4, the element identity card.
Have you ever wondered what actually makes a gold atom different from an oxygen atom? Well, it all comes down to the numbers you see here. An element's fundamental identity on the periodic table is strictly determined by its proton number, which we call Z. If you change the number of protons, you literally change the element, period. Every single atom out there with exactly 1 proton, that's hydrogen. Every atom with exactly 2 protons, that's helium. Then, if we add the protons together with the neutrons, we get the total nucleon number, or A, which tells us the atom's mass.
Next up, Section 5. Meet the isotopes.
Okay, so we just learned that if you change the number of protons, you change the element completely. But what happens if you just change the number of neutrons? Well, you don't actually change the chemical element at all. Instead, you create what's called an isotope. It is the exact same element, with the exact same chemical properties. It's just a slightly heavier or lighter version of it, simply because it has extra or fewer neutrons hanging out in its nucleus.
Let's look at a practical example to make this concrete. Hydrogen actually exists in 3 different forms in nature: protium, deuterium, and tritium. Notice how they all have exactly 1 proton in the center, that orange circle right there. That single proton is what makes them all hydrogen. But here's the difference. Protium has 0 neutrons, deuterium has 1, and tritium has 2. Because of this, they behave identically if you're, say, trying to make water, but their masses vary depending on those extra neutrons.
And finally, Section 6, releasing nuclear energy.
Now, some heavy isotopes like uranium-235 are so heavily packed with nucleons that they actually become unstable. In a process called nuclear fission, if a stray neutron happens to hit that unstable uranium-235 nucleus, it physically splits it apart into entirely new, smaller nuclei, like barium and krypton. But here is the absolutely critical part. As it splits, it throws out even more neutrons and releases a massive amount of energy. Those flying neutrons can then go on to hit other uranium atoms, causing them to split too, which creates a runaway chain reaction. Now let's contrast that with fusion. Fission powers our nuclear power plants on Earth by splitting heavy atoms apart. But nuclear fusion is the exact opposite process. Fusion involves taking very light nuclei, like those hydrogen isotopes we just talked about, and smashing them together to form a larger nucleus. But here's the catch. This requires incredibly high temperatures. I'm talking about the kind of heat you only find in the core of stars. Fusion is actually the exact process by which our sun produces all its heat and light. And believe it or not, it releases even more energy than fission does. The mind-blowing truth behind both of these reactions, whether we're splitting atoms or joining them together, is captured by Einstein's famous equation, E equals mc squared. You see, when you measure the mass of the particles before a fission or fusion reaction, and then compare it to the particles after, a tiny, tiny amount of mass physically goes missing. Where does it go? It's converted purely into energy. And because c, the speed of light, is such an astronomically huge number, when you square it, even a microscopic loss of mass converts into an unbelievably huge, world-changing amount of energy.
Which brings us right back full circle to where we started. The concepts we've been walking through today end with a really profound discussion question. Knowing that manipulating the atom can either power our cities completely cleanly or destroy our entire world in a flash of light, what responsibility do scientists actually bear for the ultimate application of their discoveries? Once you peer inside the invisible atom and unlock the power of the stars, can you, or should you, ever put that genie back in the bottle? It's a heavy question and one we are absolutely still grappling with today. Thank you so much for joining me on this explainer. I really hope this helped you see the world and the vast empty space inside it just a little bit differently.